Good afternoon, ma'am.
Any doubt from the last class?
Yes, ma'am, I tried.
Kavya, I gave you a question for the homework also.
Yes, ma'am, I tried that question.
So were you able to solve that one?
I forgot to send you, ma'am, but I tried it.
Okay.
You want me to send you now?
Sorry.
You want me to send that question to you now?
Yeah,
Answer.
yeah. So are you sure that it was correct or okay?
Ma'am,
I'm going to solve that question. Just check it by yours.
okay, ma'am.
Okay.
Yes, ma'am.
The E note that I gave you was 0.34 volt now.
Yes, ma'am.
In that question, you were given the reaction as this. Correct?
Yes, ma'am.
In this reaction, what we can see that chromium is undergoing from chromium to chromium 3 positive. Right? It means it is anode
Yes, ma'am.
and cadmium 2 positive is undergoing reduction. So it is cathode. Can I write this thing? Red cat and anodes. Correct?
Yes, ma'am.
If I write it like this, then there will be 3 electrons and there will be 2 electrons.
Yes.
So I can multiply this reaction with 2 and this with 3.
3.
Okay. So in this case, my N will be 6. Correct?
Yes, ma'am.
The E naught that you were given was 0.34 volt. Now the first part is we have to calculate delta G naught. What is the formula for delta? The direct
NFP.
formula was correct.
Yes, sir.
N is 6. F is your Faraday constant, that is 96500. And E naught you have been given. Correct.
Yes, ma'am.
This is the thing that you have to do for delta G.
Yes, I'm taught did that only.
Okay. Next thing that you have to calculate is the equilibrium constant. Correct. We know that at equilibrium, my E cell for the reaction is always 0. Right?
Yes, ma'am.
So E naught will be equal to 0.059 divided by N log K equilibrium. We have
Oh,
this relation.
yes, ma'am.
E naught given to us is 0.34, 0.059, N is 6 log K equilibrium. Got it?
Yes, ma'am.
Here only one is variable that you have to find out, that is K equilibrium. You can solve this.
Ma'am, for this I tried this formula. G is equal to minus 2.303 RT log K.
G is equal to
minus 2.303 RT log K.
You can use this one also.
That one, sir. I
Yeah.
got. Okay.
You can use that. The
Yes,
next
sir.
part that we have to use specifically the conductance electrolytic solution. The electrolytic solution that we were taking in the half cell is basically the electrolytic solution which we are dipping up our electrodes. Correct?
Yes, ma'am.
And that electrolytic solution is having some conductance. So our main goal is to understand that what is conductance and how to calculate that conductance of electrolytic solution. Conductance is basically the ability to conduct current. Can we say this, please?
Yes, sir.
Or it is the inverse or reverse of resistance. If I write resistance, then it is the reverse of resistance. Right? So the thing is that what is resistance basically? It is the opposition to
Law of current.
current flow in any electrical circuit. Can I write this thing?
Yes, sir.
Resistance is represented by R. Its unit is ohm, presented by a symbol this one. Correct?
Yes, ma'am.
We have a formula for resistance. What is it?
V by R.
R is equal to
Rho L by A.
L is the length of the conductor, A
A
is the
is the
area of
area.
conductor, and rho is resistivity.
Resistivity.
Or sometimes we call it as specific resistance. Got it?
Yes, sir.
Basically, what we said that the conductance is the inverse of resistance. Correct? So, if I invert it, like 1 by R, then I say that it will be conductance. Can I write it like this?
Yes, sir.
1 by R is equal to 1 by rho A by L.
Yes.
Okay. So 1 by R is basically my conductance. So conductance is represented by G. It is G. 1 by rho. That is again a constant that is called conductivity or specific conductivity. Inverse of resistivity is basically conductivity. Or we can say that it is specific conductance.
Okay.
Got it?
Yes, ma'am.
A by L is a constant. The constant L by A is basically our cell constant. That is represented by G star. A by L is the inverse of L constant. Got it?
Yes, ma'am.
Any doubt?
No doubts, ma'am.
Depending on the conductance, we have three types of material. We call it as we call this as with rho now. Resistivity, the symbol of resistivity, we call it rho.
Yes, ma'am.
In the same way, the symbol for conductivity, we call it as kappa. Okay. So depending on the conductance or conductivity, we have three types of materials. Insulators and semiconductors. Okay.
Yes, ma'am.
The first we have basically the conductors. Conductors are those whose conductivity is very high, means whose kappa is high. We can say that material with large conductivity are called conductors. Because kappa
Okay.
is high, then conductance will be high. Because kappa is directly proportional to conductance. Okay.
Yes, ma'am.
Example, we have metals. Insulators that do not conduct electricity, it means their kappa is very, very low. Got it?
Yes, ma'am.
Example, glass, wood, plastic. And semiconductors that have the conductivity between conductors and insulators. Means kappa lies between the kappa of conductors and insulators. Got it?
Yes, ma'am.
Any doubt from this part?
No, no doubts.
Give me any one example for semiconductors.
Silicon, germanium.
Yeah. For the conductors that we say, that example is metals basically. So the conductance that is arises due to metals, we call it as metallic conductance. Okay.
Yes, ma'am.
Why is it so basically? In metals, what is there? If I ask you that, what are the metals basically? Which block of which block comes for the metals?
D block.
D block. What about S?
S and D was.
S and D, na? Because D is the transition one. So we can find pure metals in S block elements. Okay. So S block element is basically the first and second block.
Yes, ma'am.
So what I can see over there, that in the first and second block, there are only 1 and 2 electrons in the valence shell. And they are very, very free to move because there are lesser number of electrons in the valence shell, right? So in the metallic conductance, basically, it's the valence electrons that play key role in metallic conductance. Got it?
Yes, ma'am.
Well, it's the metallic conductance that depends on various factors also. In metallic conductance, basically the electrons that moves from one side to the another one are the charge carriers basically. Metallic conductance is due to charge carriers, and that charge carriers are the valence electrons. Got it?
Yes, ma'am.
The factors on which metallic conductance depends are, it depends on the nature. which or structure of matter. Like if you are using first block element, it is having only one electron in the valence shell. And if the second block, it is having two electrons in the valence shell. Then obviously the metals from the second block will have the high metallic conductance due to the more number of valence electrons.
Yes, ma'am.
So we can say that the metallic conductance depends upon nature and structure of matter. Okay.
Yes.
Depending on the nature and structure of metal, basically, it is the number of valence electrons. More the number of valence electrons, more will be the conductor. Got it?
Yes,
And
ma'am.
its last factor is the temperature. Metallic conductance is inversely proportional to temperature. Because at low temperature, if I say that I'm having 5 electrons, valence electrons, that are responsible for metallic conductance, and they are moving to and fro in the matter. Okay? So they are free to move. That's why they are conducting metallic conductance. But if I increase the temperature, then their movement will increase. If their movement will increase, then they will disturb the movement of other particles. And if they will disturb the movement of other particles, then the metallic conductance decreases. Got it?
Yes, ma'am.
Or you can understand it like this. If I say that there are 5 members in a house, just for example, there are 5 members in a house, they are free to move here and there. Correct?
Yes, ma'am.
They have no work to do. That's why they can move accordingly. But if I increase their workload, if I say that you have to do this work, and this work, means I'm increasing their temperature. Then what they will do? They will speed up their speed up to do
Yes.
work. Okay. So
Mhm.
if they will speed up to do their complete their work, just wait, Babu. Okay. So what they will do? They will interfere in the work of others because they have to complete their work. They have to speed up. Then they will definitely interfere with the other one or disturb the other one. Correct.
Yes. Yes, ma'am.
So if they will disturb the other one, then their speed to complete the work will increase or decrease. It will decrease now.
Uh,
Because before that, they can do their work accordingly and they will be completing their work on time. But when the increase is low, if load is increased, then they will speed up and interfere with other work. And we're not able to complete it on time. So can you relate this example with this thing? Like,
Ma'am, your voice is. I cannot hear you, ma'am.
so can you relate it with how the temperature is directly proportional with metallic?
No, ma'am, still cannot hear you. Your voice is breaking.
It's still breaking.
Now it is fine.
So now is it clear that why the temperature is inversely proportional to metallic conductance?
Yes, ma'am. Right here.
Okay. It's just because on heating, the speed of the particles will increase. If the speed of valence electron increases, then metallic conductance decreases.
Yes, ma'am.
Okay. The next conductance that we have is basically the electrolytic conductance. It is also the type of conductance. Conductance we said now we have metals and one is the electrolytic conductance that is due to the presence of ions. Electrolytic conductance is the conductance of electricity basically. It is the conductance of electricity by ions. Got it?
Yes, sir.
Electrolytic conductance is also called ionic conductance due to the presence of ions. Clear?
Yes, sir.
So basically what happens with electrolytic conductance is like electrolytic conductance is somewhere related to electricity. If I have a circuit, like I have a beaker in which I have placed water in it. So what's the tendency of water? That it will dissociate into H positive and OH minus. Means the ions are present. Correct?
Yes.
Connected it with a circuit having a bulb over there and a battery is there. Okay.
Yes.
So what it will do if my circuit is complete? My circuit is complete.
Yes, sir.
Whatever the electricity I'm passing over here will help that bulb to glow. Correct? Because the current in this case are conducted due to the presence of these ions. Right?
Yes, sir.
If I place a salt in it, that is NaCl. NaCl also have ions, that is Na positive and Cl minus.
Uh-huh.
If I place salt into it now, then the intensity of the bulb will increase. Why? Because in this case, the ions that I have added will help the electrons or the ions to increase. That's why the intensity of the bulb will increase. Getting?
Yes, sir.
So basically the electrolytic conductance depends on the nature of electrolyte, like water I have added over here.
Uh-huh.
If it is weak electrolyte, then the conductance will be quite. Nature of solvent that I have added like NaCl and the size of ions. If the size of ions are quite big, then they will not be easily able to. Small size ions have higher conductivity.
Higher mobility. Yes.
And next is the solvation effect. More the
Yes, sir.
solvation, more will be the salt will dissolve in it, and the more will be solubility, then more will be the number of ions. Correct?
Yes, sir.
Next is the concentration of electron. More the concentration, more will be the number of ions and more will be the conductivity. Got it?
Yes, sir.
This is basically the concept of conductance. For semiconductors and insulators, you just need to learn that what is the definition. Okay.
Okay, ma'am.
Next, we have the conductivity of ionic solution. Is how to calculate the conductivity of ionic solution in the practical world. Like all we are talking about is the theory that we can detect it from this formula or this one, but how to measure the conductivity of a particular solution.
Huh.
Okay, as it is the ionic solution, so we have problems with this. That in the solution, how can we detect the conductivity? So the first thing, if we want to make a circuit, then we have to use the wires for it. Okay.
Yes, I understand.
So if we have to connect the wires and the battery, if we apply the DC current, then what the DC current will do? It will change the composition of the ionic solid, as it is a direct. Okay.
Okay. Yes, sir.
So that's why this problem solved by using an AC in place of DC, using an alternating current, so that the composition of ionic solution do not changes.
Okay.
Next problem is that to connect the wires in a solution. Then it is a big problem that how can we connect wires in a solution? Can we directly place wires in a solution? Please tell me.
Sorry, can you repeat?
Can we directly place wires in a solution to make our circuit complete?
No, I don't think so.
So for this problem, we use conductivity cell basically, because placing wires in the solution directly is not feasible. So we use conductivity. So now what is conductivity cell basically? A glass tube is over here. Okay. Connected by two electrodes. In this tube, I'm having my solution, ionic solution that I have to place or whose conductivity is to be known. Got it?
Yes, ma'am.
Electrode, here platinum is connected. It is basically the platinum electrode on both the sides. L is the length and A is the area of cross section. These are further connected by wire. Got it? Is it clear? Are you getting?
Sorry, we current went. What were you saying? Current went.
Sorry.
Ma'am, can you repeat, ma'am? Actually, current went here.
Okay. It is a
In the
glass
last
tube
part.
basically. It is the glass tube
Yes, ma'am.
in which we have placed the platinum electrodes on both the sides connected by a wire. This glass tube is having the length as L and area of cross section as A. And we have placed the ionic solution in that glass tube whose conductivity is to be calculated. Got it?
Yes, sir.
Now basically what happens, we have to find out the conductivity, right? So if I write that my R is equal to rho L by A, or I can write G is equal to kappa A by L,
Yes.
or I can write 1 by R is equal to kappa A by L.
Yes, sir.
If I have to calculate kappa, then L R by A. Can I write it like this?
Yes.
Okay. My main concern is to find out the conductivity. This one. For this, my L is a constant value. For this one,
Yes, sir.
A also I know that what will be the value of A. The only thing that I have calculated is the R. Got it?
Yes, sir.
In physics, you have learned about Wheatstone bridge.
Uh-huh.
Okay. So if I place this as a Wheatstone bridge, right? One is my conductivity cell is there. One resistance is this one. Is someone like this way now? I don't know. R2 is this, placed by a battery. R3 is this. It is some like this one, no?
Yes.
So if I say that R is the conductance of this conductivity cell, can I say this thing? There will be some resistance for this conductivity cell, na, as we have placed the solution in. Got it?
Yes, ma'am.
So according to Wheatstone, R1 by R will be equal to R3 by R4.
Yes, ma'am.
So from this, you can calculate the resistance of conductivity cell.
Uh-huh.
If you know the resistance of conductivity cell, so by placing the value of resistance in this formula, you can calculate the conductivity of the particular ionic solution. Got it?
Yes, ma'am.
Any doubt in this?
No doubts.
Next, we come to the molar conductivity, the concept of molar conductivity. This one is the conductivity of ionic solutions. Okay? That how do we determine the conductivity? Next is molar conductivity. It is represented by lambda m. Right?
Yes, ma'am.
Molar conductivity is the conductivity of 1 molar solution is the molar conductivity.
Uh-huh.
Okay? Or we can say conductivity per unit concentration. Can we say this thing?
Yes, ma'am.
Conductivity per unit concentration. Correct?
Yes, ma'am.
If I say that my resistance is R equal to rho L by A, right? I can write it as like this. Correct?
Correct, ma'am.
Then my kappa will be G L by A.
Yes.
Correct? So
Correct, ma'am.
L by A is my cell constant, represented by G star.
Oh,
Correct? So my
yes, ma'am.
lambda m will be what? This is a molar conductivity per unit concentration is kappa per unit concentration. Correct?
Yes, ma'am.
It is basically the molar formula for molar.
Okay.
Right?
Got it. Yes, ma'am.
Is it correct? Clear or not?
Clear, ma'am. Clear.
So first one is the conductance, where the metallic and the ionic conductance was there. In the metallic conductance, the thing that you have to learn is the temperature effect. As the temperature increases, the metallic conductance increases. Decreases, sorry. Inversely proportional.
Okay.
Okay. But for the electrolytic conductance, as we increase the temperature, the dissociation will increase. For the electrolytic one or the ionic one.
Okay. Yes, ma'am.
Okay, so as we increase the temperature, the dissociation will increase, the number of ions will increase, and the conductivity will increase. So there will be the inverse effect on metallic conductance and direct effect on electrolytic. Got it?
Yes, ma'am.
One more thing. From this formula, if I write that G star with cell constant will be equal to kappa by G, can I write it like this? Or it will be equal to kappa R, conductivity and resistance.
I
If I
understand.
have, right, if I have same cells, two same cells are there, it means the value of L and A will be same,
Yes.
correct? So if their cell constant will be same, then you can use directly the relation as this. Clear?
Yes, sir.
Next is the molar conductive is kappa by C. If you have been given the kappa in the units as Siemens per centimeter, okay,
Yes, sir.
getting that what I'm writing, that from where Siemens per centimeter comes,
No, no, understanding, ma'am.
understanding or not?
Yes, understanding.
Okay. If your kappa is in Siemens per centimeter, then the formula that you will use for molar conductivity will be 1000 into kappa by C. Got it?
Yes, sir.
If the kappa will be in Siemens per meter, then you will use kappa into 1000 multiplied by C. Got it?
Yes, sir.
Next, there is a term that is the equivalent conductivity. One is molar conductivity. Next is equivalent. It is somewhere related to number of equivalent electrons.
Okay.
It is equal to 1000 into kappa by molarity. Sorry, normality. Not molarity, it is normality, but it is equivalent. When you use this formula, when the kappa given to you is in the form of Siemens per centimeter, and when it is given in form of Siemens per meter, then you will use kappa 1000 to N. Means in place of concentration means molarity, you have to use normality over here.
Yes, okay.
Getting?
Yes, sir.
It is a theoretical part from where basically numericals comes. Now I'm giving you a question, just do it and show that one. Electrical unit of conductance, you know that conductance is represented by G and the unit is Siemens or ohm inverse.
Yes, the moment was for that.
That you know, or do I need to tell you this?
I know, ma'am.
The electrical conductance of a column of 0.05 mole per liter NaOH solution of diameter 1 centimeter and 50 centimeter, 5.4, 10 to the power 3. Okay. So you have to calculate resistivity, conductivity, and molar conductivity. Okay,
Okay.
just do it. The first thing that you have to do is the diameter and length given to you is in centimeter. So you have to convert the electrical conductance of a concentration of solution is given to you in mole per liter. So you have to convert it into mole per centimeter.
Okay.
Correct? As
Yes,
it
sir.
is mole per meter cube, na?
Uh-huh.
So you have to convert it into mole per centimeter.
Okay.
So you have to divide it by 1000.
I do it. Got it, ma'am.
Done?
Yes, ma'am.
Just send me a clip.
Okay.
Just send me a check.
Extend on.
Have been given the conductance now.
Sorry?
You have been given electrical conductance of a column as 5.55 to 10 to the power 3 ohm.
Resistance is that, no?
Yeah. That is the resistance. But here I have written the conductance now.
Actually, I saw the unit and I took it as resistance.
If you show the unit, then it considers as well. Otherwise, you have what you will do if just do it if I change its unit as ohm inverse.
Okay. Nothing. G is equal to 1 by same.
You have calculated the resistivity, Kavya, in the question
Yes, sir.
81.135. Conductance you have not been asked in the question, no? That is the G that you calculated is 1 by R. You have been asked the conductivity.
Okay.
What is conductivity?
The ability to conduct.
The formula one.
1 atom. I'm recollect.
Conductivity is the inverse of resistivity. So if your resistivity is coming out to be 81.135, then conductivity will be 1 divided by 81.135.
So that's what I did now.
No, you have, but you have written 1 by R and G, na?
Acha,
Formula you
formula
have,
में formula I wrote wrong.
yeah, you have done the correct thing. And one more thing, you have to mention the units always.
Okay.
Okay. Why have you used the formula 1000?
Because you usually don't have to divide by 1,000 mole.
But it is
Mole
in
per.
Siemens per centimeter, na?
I don't know. Like,
What do you have used kappa over here? And what is M? Mention it also.
I'm dotted with the conductance also.
Okay, but just tell me that what is the kappa and the concentration that you have in the question that you sent me. You have directly written the answer that is 229.6.
Kappa is 0.0114, and M is 0.05.
Point.
Kappa is 0.0148 and M is 0.05.
But I have told you na, that it is mole per liter. And the
हाँ तो
units that are used.
इसलिए I put 1000 up, right? Conversion के लिए.
Okay, correct. Okay, correct.
Yes.
This is the class. Just practice for these types of questions related to conductance and resistance. Tomorrow we will
Yes.
start with the one topic is left from this part, that is the strong electrolyte and the weak electrolytes are there. And then we will go with electrolytic cell. Then your
Okay.
electrochemical cell will be covered.
Yes, ma'am. Okay.
If you are having any doubt, then you can.
No doubt, sir. Thank you.